Hey everybody, welcome to this interesting session on matrices and determinants, which is one of the key topics in linear algebra, right? And most of the students get intimidated by this because they do not know how to proceed with the basic concepts. But this video is intended to do exactly that. So without wasting much time, let's get started. Let's take a whiteboard and try to understand what a matrix basically is, right? So there are two things in today's topic. One is a matrix, and the other one is a related topic, that is a determinant. All right. So to get an idea of what a matrix basically is, let's draw a new coordinate system here, right? So your x coordinate and your y-axis, right? Your x-axis and y-axis. And then let's say you have a point in the x-axis which has, say, coordinates 2 and 1. So this is basically 2 units from the origin, and this is 1 unit from the origin in the vertical direction. So 2 units in the horizontal direction and 1 unit in the vertical direction. That the point is 2, 1, right? This point. Now, when you say that the coordinates of this point are 2, 1, it basically means that it's 2 times the unit vector in the x direction. And this is 1 times the unit vector in the y direction. Now, this is a very important concept called as the unit vector. So what is a unit vector? As the name implies, unit. The magnitude is 1, right? And the direction is the direction of the axis itself. So the coordinate of a point in any axis is basically given by the scale multiplied by the unit vector. So this is 2 units multiplied by 1 in the x direction and 1 unit multiplied by 1 in the y direction. And in a matrix form, if you want to represent the coordinates of a point, or maybe the coordinates of the unit vector, it's like 1, 0, that's the unit vector in the x direction, and 0, 1, that's the unit vector in the y direction. So in matrix form, we represent that as 1, 0, 0, 1. And this is also called as a unit matrix, right? As simple as that, right? Now, say, for example, for some or the other reason, suppose you want to stretch the unit vector in the x direction by, say, 3 times, and the unit vector in the y direction by, say, 2 times. So your original coordinate system is going to look something like this, where this unit vector gets stretched 3 times. So anything in the x direction also gets stretched 3 times. Like your point 2, 1 becomes this, 3 times. And your point 1 becomes 2 times, this and this, right? So suppose you stretch this unit vector by 3 times in the x direction and 2 times in the y direction. How would you represent your unit matrix then? It basically gets transformed to something like this, right? 3, 0, 0, 2. So anything in the x direction is now getting stretched 3 times. So your original coordinate, which was 2 in the x direction, has become now 2 into 3 equals 6, right? And then your original coordinate in the y direction, which was 1, has now become 1 into 2, which is 2. So now your point 2, 1 has somehow transformed to 2, 4, 6. 6 and then 1, 2. 2, something over here. So this point has now become this point, right? 2, 1 has now become 6, 2. So in matrix format, we represent this as 3, 0, 0, 2 multiplied by 2, 1 gives you 6, 2. And then you might have learned this in school and college that the way you multiply a matrix is basically you take 2 into 3 plus 1 into 0. 2 into 3 plus 1 into 0, which equals 6 plus 0, which equals 6. And then you take the same 2 into 0 plus 1 into 2. 2 into 0 plus 1 into 2, which is basically 0 plus 2, which is basically 2. So 6 and 2, which is basically 6 and 2. And that's exactly what we got even by using the analytical method. So this is basically a matrix transformation on this original coordinate system, which was like 1, 0, 0, 1. And we have transformed that to a 3, 0, 0, 2. So basically, we are trying to address here that if you transform your original coordinate system, which was 1, 0, 0, 1, to 3, 0, 0, 2, then what's going to happen to the coordinate system of any point, say 2, 1, in the original coordinate system? We get the answer that it becomes 6, 2. So the 6, 2 is nothing else but the coordinates of the point, the coordinates of the original point in the original coordinate system, which has been transformed to 6, 2. So 6, 2 is basically the coordinates of the same point in reference to the original coordinate system. All right. So if you transform this point 2, 1 by applying the matrix transformation 3, 0, 0, 2, the coordinates of the point with reference to the original coordinate system become 6, 2. That's the meaning of a matrix transformation. Clear? Right? I hope this is easy to understand, right? Let's take another example. Let's say you have a point 0, and this is x, this is y. Let's say you have a point like say 3, 4, right? It's actually going to be something like this. 3 units from here and 4 units from here, right? It's 3, 4. And if we subject this point to a matrix transformation, it's actually the coordinate system which we are subjecting to a matrix transformation, right? So let's say 2, 0, 1, 4. This time you see that this is non-zero. It's 1, 4. So what's going to happen to this point? So 3, 4. So what we do is 3 multiplied by 2 plus 1 multiplied by 4. That gives us 6 plus 4 equals 10. And then 3 multiplied by 0 plus 4 multiplied by 4 gives us 0 plus 16 equals 16. So the new coordinate system of this point becomes 10, 16. All right. So you can verify this analytically as well. Suppose if you actually try to geometrically view this transformation, what you're basically doing is 2, 0 means that your x-axis, which was like 1, 0, now becomes 2, 0, which means it's nothing, it's the same 0 in the y direction, but the x direction has been stretched by 2 times. So anything in the x direction gets stretched 2 times, right? So x-axis now becomes something like this, right? And your y-axis becomes now 1, 4. So now there are two things happening here. Your y-axis is now being shifted 1 unit in the x direction as well. So like this becomes like this, 1 unit in the x direction. And 4 basically means that it's becoming 4 times in the top direction. Like this is becoming, let's see, 1, 2, 3, and 4, right? So 4 times there. So it's going to basically look like something like this, right? 1 unit here and 4 units at the top. So your original point, which was here, has now gone something over here, right? It's because of the small change here. It's not only about moving the axis in their respective directions, it's also about adding a 1 unit coordinate to your y, which is in the x direction. So to your original x, which should have ideally become like 3 into 2 equals 6, right? You also add a 1 into 4 to that because this is shifted here by 1 units, right? I hope this is analytically clear, right? So that becomes 10. And your y-axis, which was like 4 units here, since you're moving it upwards by 4 units, it's becoming 4 into 4, which is 16. So it's 10 and 16. Clear? So that's the idea of a matrix. So matrix is nothing else but it just shifts your orientation of the coordinate system, right? It's just another way of looking at. So if you want to stretch something, or say if you want to rotate something, or say if you want to be mirroring something, it's a matrix which gets that done for you, right? So now a parallel concept is determinants. Let's see what they are. So what is a determinant? So we have all learned this in school that if you have a matrix, say A, B, C, and D, this determinant is given by two horizontal bars, A, B, C, D, which basically equals AD minus BC, right? This is something which we have all memorized and marked up from school and college. But then what's exactly the meaning of a determinant in reference to a matrix? What does that basically imply geometrically? Let's see that. Let's say you have your original coordinate system, right? X and Y. And your unit vector looks like this, which is basically 1, 0, and 0, 1, right? So it's a 1 by 1 square. Now, suppose you subject this to a matrix transformation, A, B, C, D, right? For simplicity, let's assume that B and C are 0. So this becomes A, 0, 0, D, right? So which basically means that now 1, 0 has become A0, right? So anything in the x direction gets stretched by A units, right? And anything in the y direction gets stretched by D units, right? So original unit matrix square has now become something like this. This is A, and then this is D, right? So the area of this rectangle is A multiplied by D, which is basically AD. Now, if you ask yourself a question like, how much has my unit square increased in area? What is the increase in area of my unit square? Is basically nothing else but the area of this matrix, area of this rectangle divided by the area of the unit square, which is 1 into 1. Nothing else but AD. And if you compare this AD is basically AD minus 0 into 0, which is basically the determinant. AD minus 0 into 0, because B and C is 0 here, right? So determinant is nothing else but it's the scaling of the unit square because of your matrix transformation. It's as simple as that, right? So suppose you subject your original coordinate system to a matrix transformation of A, B, C, D. A determinant basically tells you by how much is your original unit square being scaled by. So like your transformation, suppose it's now going to look like this. So x now becomes x dash, which looks like this. And your y becomes y dash, that looks like this, right? So unit square, which was like 1 by 1, is now going to look like a parallelogram like this, right? So what is the area of this parallelogram compared to this unit square? So this is going to be your D. Sorry, this is going to be your C, right? Because it's AC. This is going to be your B. And then this is going to be your D. And then this is going to be your A, right? So this can be geometrically proved that the area of this parallelogram equals AD minus BC, right? So that's basically the idea of a determinant. All right. So it's not just that you doing this for fun or something. There's basically a purpose behind that, right? There's basically a mathematical meaning to it, a geometrical meaning to it, right? So if you visualize this parallelogram, you get the entire idea, right? So I hope you like this session, and I hope you appreciate the session. And now you're in a position to understand what's basically a matrix and a determinant. So I hope you enjoyed this session. And for more such insights, please feel free to write to me and reach out to me, right? So thank you so much and catch you in another video. Thank you. Bye-bye. If you like this video, please press the like button. For more such videos, subscribe to the channel. If you have suggestions for a new topic and would want to see a video made on that topic, please feel free to comment in the comment section below. Thanks for watching the video and see you in another video. Bye-bye.